We have this afternoon Volk from Reconstruction, and he's going to talk about tensor decomposition beyond Tensor.
All right, yeah, thank you for coming. So maybe just a few comments here. This is a joint work with Shir, Peleg, and Amir Shpilka from Tel Aviv. I guess the same comment because several people have asked. So back in the old days, you would have to type the title of your talk to Google Images and hope that something relevant would come up. But now we have tools like DALL-E 2, so you can just write your vision into existence and get artwork for your slides. And I guess the third comment is that this talk will share some similarities with the talk which was gave 2 days ago, I believe. But I will not assume you remember a lot. So I mean, I will not assume any special knowledge. And in fact, I want to start sort of like at a higher level. And which was mentioned, algebraic complexity. And so what is even algebraic complexity? What is it that we study there? So what we are trying to study is algebraic algorithms, how strong they are or how weak they are, what's going on. And the most general model of algebraic algorithms is an algebraic circuit, which is just a way to model your computation as a graph. So you start with variables or constant from a field, and then you can apply arithmetic operations on them. So you can add two things that you have, you can multiply two things, and then you can iterate that and so on. So each node here computes a polynomial in a natural way. If it's a sum gate, it computes the sum of the children, and if it's a times gate, it multiplies. And at the end, you get some polynomial. And this is how all the algebraic algorithms that you know look like. All the algorithms for matrix multiplication, for determinants, for things like FFT, whatever, they are all, even if you don't present them like that, when you teach them, they're all really just algebraic circuits. So what kind of questions do we want to know about algebraic circuits? I guess the first question is upper bounds. So we want to obtain good algorithms, for example, for matrix multiplication. That's a big problem. And then there's the analogous question of lower bounds. We want to show that some explicit polynomials are hard to compute. They cannot be efficiently computed. This is, you can think of it as an algebraic analog to P versus NP. P versus NP is the question of showing that some explicit problems are hard to compute. So of course, P versus NP is like the most important question in the world that was ever asked and so on. And in algebraic world, it's a more important question about algebraic computation. So as an example, I mean, the canonical example you should have in mind is the permanent polynomial, which is explicit, and we don't know how to compute it efficiently. And we believe that it cannot be computed efficiently, but of course, proving it is a big deal. So that's the lower bound question. Another interesting question. Oh yeah, maybe I should. Yeah, before going to the next question, I should point out just it's not relevant to this talk. It's just in the topic of in the theme of this workshop. It seems apt to mention that one of the approaches for proving lower bounds is to show good lower bounds on tensor rank. So it turns out that lower bounds on tensor rank imply lower bounds on algebraic circuits. So I guess you don't need extra motivation to work on tensor rank lower bounds, but if you do, then here's one. So yeah, that's maybe also why it is so hard to prove lower bounds on tensor rank. Yeah, so let's move on to the next question, which is what we call identity testing. So now we are given an algebraic circuit C, and we want to decide if it computes the zero polynomial, if it's an identically zero polynomial. This is very easy to do with randomness. And how do you do it with randomness? You just plug in random numbers, and you can evaluate the circuit efficiently. What you cannot do is expand all the polynomial, right, monomial by monomial, because that could have many monomials. So that would take exponential time. But just plugging in random numbers and doing the computation, this is easy. So this is a problem that it is easy to do with randomness, but we don't know any way to do it deterministically, which doesn't run in exponential time. So this is like this is the ultimate de-randomization problem in algebraic complexity, and also in general, you could say. This is also related to lower bounds. Again, giving good algorithms for this problem also implies lower bounds for circuits. It's kind of I guess some of you have seen it. If you've never seen it, it's weird that some problem being easy implies that another problem is hard, but nevertheless, it's true. And the last problem, which is the focus of this talk, is the reconstruction problem. So this is analogous to learning in Boolean computation. So now we are given a black box computing a polynomial. We can evaluate it on inputs that we pick, and we want to learn the circuits. So we will soon explain what learning means. Basically, we want to output a circuit computing the polynomial which is hidden inside the black box. This is well, here it's randomness, or I mean, it's not clear what to do even with randomness. It's it doesn't seem like an easy problem. We'll soon see that it's in fact a hard problem. But yeah, so unlike identity testing, which was easy with randomness, this is hard even if you allow randomness. Good. Okay. So let's talk a little bit more about the reconstruction problem again. So we have a box which is black, and so you cannot see what's inside. But there is a polynomial inside. What you can do is interact with it, like you can give some alpha and you get f of alpha. There's no, there's no, I mean, there are models like where there's no lying, or nobody's trying to fool you, right? It's not one of these questions. I mean, there is a polynomial inside, it computes f, you get the correct thing. And yeah, you want to output a small circuit computing f. Of course, you can always, given enough evaluation, again, you can always learn the entire polynomial, monomial, you can interpolate the polynomial, but that would take exponential time. So we want to do something efficient. Yeah, like I said, analogous problems in Boolean complexity are also very well studied in computational learning theory and so on. And so usually it's useful to assume f is not just arbitrary polynomial, but it comes from some class C of circuits that are limited in some sense. And then there's the question of what do you exactly require from the output? Do you require that the output also belongs to the same class, or maybe you allow to learn from for a larger class and so on. So you can define whatever is convenient for you. If we insist on outputting something from the same class, in the terminology of learning theory, it's called proper learning. Another issue is like whether you insist you output the absolute smallest possible circuit for f, or maybe you are satisfied. Obviously, for many applications, it's fine to just output something which is small enough, maybe to within some bounded function from the possible smallest thing. So I mean, for every set of answers to this question, you get slightly different models, and they all make sense. There's no one right model here. Right. So, like I said, the problem is pretty hard. We'll soon see why. So we focus on weaker models. We assume that what's hidden in the black boxes comes from some limited class on algebraic computation, and we say, well, maybe if this class is so weak, then maybe we can do something. But like we shall soon see, even for weaker classes, it's not. You get non-trivial questions. So what is the class that we will consider? And this is a class that Fish was also presented. So we're talking about circuits that have depth 3, and the top sum gate. I should just use my finger. The top sum gate has k inputs. So this is called the top fan-in in circuit terminology, and think of k as something small. So why is that thing? So these triangles compute linear functions. So you have a sum gate that's connected to the input, and then you have one level of multiplication gate, and then you have one level of sum gates. This is the model. So for obvious reason, we call it sigma pi sigma. And then this k there in the exponent is supposed to remind us that the top sum gate has only k things entering it. It's somehow in some senses it's the I mean depth 2 is usually there's not a lot you can do in depth 2. You can just sum monomials. So depth 2 is, you can compute sparse polynomials. Depth 3 is already very non-trivial. We don't fully understand what's going on in depth 2. And bounding this top panning is maybe like sort of like the weakest non-trivial model, or one of the weaker non-trivial models one could imagine. Yeah. So is everything clear so far? Or, okay. Good. So maybe let's explain again how this is connected to tensor rank. But I mean, we've already gone over this. So the circuits compute a polynomial which are the sum of k things, and each thing is a product of linear functions. And in general, you can restrict it even further, and people have, and you can study models where you can like powering circuits where the multiplication gate is all the multiplication gates are just powering gates. So they have a single linear function as an input, and they just take it to the power b. You can consider, okay, so here there's a slightly unfortunate clash of terminologies. So in algebraic complexity, when we say multilinear, we just mean that the individual degree of every variable is 1, as opposed to set multilinear functions, which is what other people call multilinear functions, where you have this partition into these sets, and each monomial contains one variable from each of the sets. So you can consider set multilinear circuit. And another thing is to distinguish between restriction on the circuits and restriction on the polynomials. So you can compute multilinear polynomials using circuits that are not multilinear. In fact, if you try to think how you compute determinants, so the efficient algorithms for determinants are circuits that are not multilinear. They compute things that are not multilinear, and then somehow in the end, everything cancels out in a magical way, and we don't know. So a circuit is multilinear if everything you compute along the way is multilinear, and we don't know how to compute the determinant in a multilinear way. And we believe, well, I don't know. Some people believe that it shouldn't be possible, that it requires exponential size. So just to emphasize, I mean, here we require things from the circuit. So I mean, also here you can imagine some multilinear polynomial that is computed in a non-multilinear circuit. But when you say a multilinear circuit, for example, you insist that in each multiplication gate, the linear function that it multiplies have these joint supports. So there's nothing, no x squared appears that is later canceled out somehow. And set multilinear thing is exactly the same thing, except again, you have the partition to these sets, and each product gate multiplies function on the x1 variables times a function on the x2 variables, and so on. So I've said a lot of things. I hope I didn't confuse you, but okay. So the connection to tensor is just that if you have a tensor, which is for me just a set multilinear polynomial, it's just a different way to say the same thing. Then every this set multilinear product is just equivalent to a rank 1 tensor, which means that if you can compute this polynomial with a sigma pi sigma circuit with a top fanning k, it's just a different way to say that the rank of this tensor is at most k, because you sum k rank 1 tensor and you get the polynomial. So it's just I mean, just saying something which is completely equivalent in a different language. So I hope it's not confusing. All right. I mean, one corollary is that if you insist on proper learning, because computing tensor rank is hard, if you insist on proper learning of sigma k pi sigma circuit, where you insist of outputting the smallest k, then it's an NP hard problem. So we have to manage our expectations regarding what we can and cannot do. Good.
Which fields are you working?
Yeah, so well, I mean, it makes sense over any field. I didn't present any theorem so far, but I mean, let's just assume a field is complex numbers for this talk. With, I mean, the things I will present, they work over other fields. They just need to be large enough, and if they're not large, just take an extension and work over that extension. Yeah. So yeah. So you can ask, I mean, is it always hard? Maybe you can approximate. Maybe there's also some. Yeah, I guess this came up earlier in the talk today about some notions of average case, which we will not deal with it in this talk. But turns out it's not always hard. So the work Vishwas was talking about 2 days ago shows that you can learn these circuits or reconstruct these circuits, and the algorithm runs in time, which is roughly n to the power t of k, where t is for terrible. It's a terrible function of k. I mean, I'm not trying to insult anyone. I mean, we'll have more terrible functions soon. But so t in this talk here, whenever t of k, it will be some highly fast-growing function of k. It will not be the same t every time. It will be different functions. And it's not, when I say, you know, terrible, it's not that terrible. It's like a exponential, like maybe 3 times or 4 times exponential in k, but it's not like something, you know, that's functions in the world. I just don't want to deal with writing that many superscripts. Yeah, so I mean, in particular, you know, when k is constant, this is something you can learn in polynomial time. So it's not always hard, right? When the rank is constant, is you can do it. Yeah, they also get similar results for for powering circuits and for which is the model again where the product gate is a power gate, and for multilinear circuits, which is the model where every product gate compute just multiplies disjoint linear function with disjoint supports. So yeah, so that raises the question: can you get something for k which is super constant? And we answer it in the affirmative. So we get algorithms that are well, for, I mean, yeah, again, for all these models where the running time is some, again, different, even more parallel function of k, but times polynomial in n. So for some small constant k, this is still polynomial time. Okay, I guess you can ask well, why? So okay, so what? Right? Why did you even bother to do it? I guess the first answer, if you're familiar with the language of fixed parameter tractability algorithms, then this is exactly this definition. Like you want to sort of separate the k from everything else. And the other motivation is the connection to tensor rank. So you can ask, I mean, which tensor rank is hard, it's NP hard to compute. But when does it become hard? Hostad famously proved that even for 3-dimensional tensors, it's hard to compute. It's NP hard to compute the tensor rank. And then there's a theorem of Shitov showing that, I mean, characterizing exactly. So it's as hard as it actually works even not for field, but maybe for rings or maybe some assumptions. It's as hard as solving polynomial equations over the ring. So for the integers, it's undecidable, and for the reals, it's p-space complete, something like that. So it's even, the point is that for sometimes it's even harder than NP. So it's a pretty hard problem. And it's even hard to approximate to some tiny constant factor like 1.001 or maybe something a little bit more. So it seems hard, but all those, I mean, all the constructions we have give, at least for type tensor, when you do the reduction, the hard instances are those where the rank is high. And then there's a question of when does it become hard? Like, is it like when the rank is low? is still hard. So Vishwas with Shubangi and Ilya showed that it's not hard when the rank is constant, and we show that it's not hard for some super constant function. And now the question is, and I will mention it in the end in the open problem, like the question is like to bridge this gap between I mean, this is a very small function. It grows with n, but very slowly, and it's not close to n. But it's interesting to figure out what's the truth here. Where's the hardness? Okay, good. Maybe this is a good. I mean, so okay. So my plan is to present. I mean, I will sketch the algorithm by Bhargava, Saraf and Volkovich, and then I will show how we improve this. But if maybe there are questions, it's a good time to take a second and.
So you do allow to take algebraic extensions of your graph.
Yes, but maybe you can just think of the field in complex numbers if you don't want to worry about it. Oh yeah, I mean, yeah, for undecidability, yeah, there's no, I mean, yeah, if you give a tensor over the integers, we are allowed to work over fields. Okay, yeah, so I want to explain I want to explain the BSV algorithm, and then we'll sort of run into some issues, and we'll develop some more theory about it. But it's easier to start with the algorithm and then see what we need to show. So, like Vishwas showed, we sort of let's start with assuming that the degree is very low. That the degree of the circuit is which we know by D, and let's assume that it's very small. So K is the K. There's one K, which is the top fanning of the circuit. And D is the degree. And M would be the number of variables, total number of variables you have.
Okay.
Okay. So let's start with assume that the degree is small. So we have again a depth-free circuit, and each product they multiply at most D things because the degree is at most D. And there are at most K multiplication gates. So up to some linear transformation, which you can find, the total number of variables you have is at most K times D. And again, we assume D is small, so this is a circuit that computes a polynomial in a small number of variables. And this linear transformation, it's not hard to find. There was some contentious discussion about it in the talk by Vishwas, but it's this algorithm by Karini, and then I think Alessandra, you mentioned that it's known. I mean, it's not surprising that it's known even before that. It's simple. It's just computing kernel of some matrix, basically. So now what do we do? So let's just assume the number of variables is small. So how can we handle this case? And the idea is to first just interpolate the polynomial in the most barbaric way you can think of. You just evaluate it at enough points, and you write it as sum of as many monomials as you have in m variables of degree D, and you just write it monomial by monomial. So now you have the entire polynomial, and now you add the constraint that this polynomial has a small sigma k pi sigma circuit. So you just imagine there's a circuit that has all the possible coefficients of linear function as variables, and you solve for the polynomial that you know should have the circuit. So you just set up this system of polynomial equations, and you solve it. And solving a system of polynomial equations is not an easy. It's not something we can do efficiently. But since we assume the degree is small and the number of variables is small, this is something which is within our budget to do. It's some, again, terrible function of k, but we can allow ourselves to do it. So it looks like we are done, except there is some small issue that we wanted. I mean, we start with a multilinear circuit, and when we do this linear transformation, it doesn't necessarily preserve the multilinearity of the circuit, because now we replace every variable with a linear function, and when we do the inverse transformation, we can get things that multiply x by x. So you do some other stuff to deal with it that I won't get into, but it's just adding some extra polynomial constraint to ensure that this doesn't happen. And if you only care about set multilinear circuits, which is relevant to tensor, then it's not an issue there. So we don't have to worry about it too much. But it's an extra thing you can do. And the total time that it takes, if you work out the details, is something which is polynomial in n and d to some function of d and k in the exponent. And this is also something we improve to something which is just polynomial in d. But I won't, like I said, I won't talk about it. It's not very difficult, and it's not that interesting for this talk. So let's not worry about it. And like we said, just assume that d is bounded by some function of k. So this entire expression is just a function of k. N is the number of variables. So the circuit computes an n-variate polynomial. But what we don't want is anything that depends on k to appear in the exponent of n. That's the yes.
N is the number of variables. So what is n?
So okay. So what you assume is that the circuit has n variables, and then you say, well, after a linear transformation, I mean, you can find a linear transformation such that it just has n variables. So it's an n-variate polynomial. It's an m-variate polynomial, which is masquerading as an n-variate polynomial.
Which one is it?
M is very small. M is at most some function of k, and n is very big. So, if I give you the circuits that compute x1 plus x2 plus xn, then you can take a linear transformation and it becomes a polynomial in just one variable, right? Yeah, maybe I should have written somewhere the parameters more clearly, but yeah. So this is what you do when the degree is very small, but of course that's not the difficult case. And so when the degree is very high, what you want to do is sort of partition it into a sum of what we are going to call clusters, for reasons that we will soon see why. And you want to say, well, each cluster would have low degree. So then I would learn each cluster separately, and then I would just sum them. Except it seems very strange thing, because how I mean, yeah, like I said, I mean, it isn't like how can you write a high degree thing as a sum of low degree things? It doesn't make any sense. Yeah, and then there's a question of, yeah, how can you do it, and what are clusters, and how do you find them, and so on, and what clusters implies some distance measure between things. So we need to define all those things, and then we will have to explain how we just have black box access to F, not to anything, any clusters around it. So we'll need to explain what's going on there. So let's do it. And this is also a concept that came out in Vishwa's talk. So I want to define the rank of a circuit. And we will start with a wrong definition, but then we will amend it. So suppose C is the sigma pi sigma circuit. And I want to define the rank. I'm going to call it the syntactic rank for reasons that will later be clear, to be just the dimension of all the linear functions that appear in the circuit. Okay, again, this is an incorrect definition. There will soon be corrections. But this is the rank, just the dimension of whatever linear functions you have. And maybe before we see how to correct it, we'll explain what is the theorem. Like, what's the motivation for this definition? What's the theorem we want to prove? And then we will see how to correct it using the theorem. So people proved it because they wanted to do identity testing for these kind of circuits. And the theorem says that there is some function that depends on k, r of k, the rank bound for sigma k pi sigma circuit, that every identically zero circuit, such circuit, has rank at most r of k. Right? This is the theorem. And this was, I mean, first proved by Dvir and Shpilka with a very large, with some r of k, which is, I think, exponential in k, but this was slowly improved. And then the last works by Saxena and Shadri show that r of k is like k squared, something like that. Except that, well, this theorem is not true under the current definition of rank. Because why is it not true? Because you can always take an identity on a small number of variables and now just multiply it by a bunch of linear functions on more variables and increase the rank, right? And zero stays zero. So let's not allow this. Let's define a rank of whatever you get. So you have a circuit and you factor out the GCD, which are the linear functions that appear in all the multiplication gates. You toss them out, and whatever remains, this is the rank. Right? Is this clear? So again, you have a, maybe I should write. Oh, I don't want to.
There's another board.
Okay, let's do it here. So you have these sum gates, and then there are multiplication gates here, k of them. So just if there are linear functions that appears in each and every one of them, I throw them away, or up to a multiple by scalar or something. I just throw them away, and whatever is left, this will be the rank of the circuit. And now the theorem is almost true, except there's still one more way to cheat, which is I can like add and subtract something which is has high rank, which is also not interesting. So the theorem is true when you add the word minimal, and minimal just means that there's no subcircuit that sums to 0. So now this is a definition and a correct theorem that there is some rank bound for sigma k pi sigma circuit, which is a function of k. I mean, it's almost there's one tiny little I left, which is over some fields, this function has some very mild dependence on the degree, but not over the complex numbers. So I mean, let's not worry about it. So yeah, so if you define rank in that way, then every minimal sigma k pi sigma circuit has bounded rank. So really, these depth tree identities are very, very limited in what they can do. So yeah, so the reason they define it is that using this theorem, you can do identity testing for those circuits in time, which is n to this function in the exponent. And again, if k is small, this is efficient. Because you basically, again, you apply linear transformation, you get a circuit on a very small number of variables, and you do some trivial brute force thing to check for zeroness. So yeah, this is the reason they define it, and this is the theorem that they can prove. And another tiny observation that multilinear circuits multiply things with disjoint support, so they are linearly independent. So so the rank is at least, or is also at least the degree of the circuits, right? Because if you multiply 3 linear functions that have disjoint support, then the dimension is at least 3. Well, it is 3, but you can have more stuff. So you can use the low degree algorithm also for low. If you know that it's low rank, you can sort of factor out the GCD and run the algorithm on this low degree stuff that is left. Okay, are we? All right. So now we have this definition of rank. So I want to explain what are those clusters. So let's denote the multiplication gate by mi. So I write it as sum of mi, and I'm going to define a partition of those k multiplication gates into S clusters, C1 through CS. So it could be that these two are in a cluster, and then this thing is in a cluster, and this thing is a cluster. And what it means, a cluster means, is that the rank of every cluster is small, and the distance of every 2 different clusters, which is just the rank of this subcircuit, for example, is large. Right? So this is why it's clusters, because you take all the multiplication gates, you sort of group them to say things that are close in this rank measure and things that are far. Right? This thing, it really defines. It actually defines. You can show that it defines a distance function on the multiplication gates. So again, we want to take the multiplication gates and sort of group them into things that are small in the sense that their total rank is small, but the distance between every 2 different things is large. This is a way to partition the circuit. And yeah, like I said, this is really defining a distance measure on the cluster. And the nice thing is that there's a way to find those clusters. So there's an algorithm that if you get the circuit, now you actually need a circuit. It's not a black box thing. You actually get the entire circuit, and you look at the multiplication gates, and you're able to find those clusters. So you also get this tau. Tau was the parameter that controls the how far two different things are. So you get a circuit and you get tau, and this thing finds you clusters. And oh yeah, this is a typo. It's supposed to be R. I mean, well, yeah. Okay, yeah. Sorry. I mean, it gives you some clusters with low rank, where the rank would depend on K on tau. And it also has the interesting thing that this partition is unique, meaning that every two circuits computing the same polynomials will have the same clusters. I should point out that they would have the same cluster in the sense that the cluster will compute the same polynomials, but they don't have the same syntactic rank because the rank depends on the circuit, not on the polynomial. And the reason I'm pointing this out is that actually well, an interesting story there where this theorem, the theorem was appeared in the paper of Karnin and Shpilka, but the proof had an error in it, which went unnoticed for some years, and we fix it. So now it's fine. Oh, so yeah, that's a different thing. So okay, yeah, maybe just to wrap up this story, there is a way to partition the circuit into clusters, and this way is somewhat unique in this sense written here. Okay, so now after having done all that, we need to continue to explain the algorithm. Right? We said we're going to sort of try to partition our circuit into clusters and learn each cluster and then lift it back to the thing. Yes.
Just to clarify, this tau supposed to be something small. In the previous version.
Yeah. What thing?
The tau.
The tau is some function of K. I mean, but it's yeah, it's not too large, but it's still enough to distinguish between this case and this case. Yeah, let's not worry about what tau is exactly. Eventually you just set it to whatever you need. All right, yeah. So like I said, we can learn a cluster, except that we don't have the circuit, right? That's what we are trying to do. So what we're going to do is just to project into a small subset of variables and just learn everything there, and then try to lift it up to the entire variable. So let's just have this notation of f restricted to b and alpha, which is for b the subset of a variable and alpha is some vector, and you keep the b variables alive, and you set everything elsewhere according to alpha. And then really the entire BSV algorithm, well, you know, it takes a lot of work, but really the idea is that you show there's some b, small b, that preserves the structure of the clusters, in the sense that the cluster of the restriction is a restriction of the cluster of the original polynomial. You learn the cluster of the small polynomial restricted to b, and then you also need to do some other stuff. But this is the high level idea. But you can see that just guessing the set b would require time, which is n to some function of k. So this is not something we would want to do. We would want to sort of finding this we would want to find this set efficiently, and not just go over all possible choices. But even proving that there's some b is not a trivial statement, but it's true. All right, how are we on time? Yeah. Good. So yeah, like I said, what we want, the main thing we want to do is now is have an efficient way of finding the set B. And the natural way to do it is to start with the empty set and just add some variables and try to see what's going on. I mean, each time you add a variable, you figure out the cluster, you see if something has changed, maybe you need to modify it, and so on. But the thing is that if you remember, the thing what I try to emphasize is that if we work with the syntactic ranks, the syntactic rank depends on the circuit, and each time I add a variable to B, I have a new polynomial, and I try to learn it, and I get a different circuit. And now the ranks can completely change. It's not clear what the relation between the new thing I got, the rank of the new polynomial and the ranks of the old polynomial, because each time I learn a different circuit and the rank really depends on the circuit. And that sucks. So, so the solution is to define a different notion of rank, which is semantic, in the sense that it depends on the polynomial and not on the circuit. So what we want to do is define a semantic notion of rank, which we will soon see will be very similar to the syntactic, except that it's a property of the polynomial and not of the circuit. So there it is. What is semantic rank? Is you have the polynomial f. If it has linear factors, you throw them away, you just ignore them. And now the rank is the minimal R such that you can write the polynomial as a polynomial in R linear functions, right? So let's assume there are no linear functions, so the rank is just the minimal R such that the polynomial is, you can do a linear transformation and you get a polynomial in R variables. That's a different way of saying that. So you can see it's inspired by the syntactic rank. It's always well, we'll soon see how it relates to the syntactic rank. But the important thing is that it's a property of a polynomial and not of a circuit computing the polynomial, which makes it convenient, but it also has some downsides because I mean, there are many technical issues that I won't get into it at all, but many things that were very easy to prove for syntactic rank are now not impossible to prove, but just very annoying to prove. Yeah, I mean, we won't get into it at all. But yeah, so what are the relations? So I mean, it's very easy to show that the semantic rank is at most the syntactic rank, but there's also inequality in the other direction, where one could show they are not too far apart. So the syntactic rank is at most the semantic rank times some correction factor that depends on k. And this is well, this also already makes many things make life much easier. There are many things that you can prove for syntactic and then just translate them to semantic using this relation. So everything I said about the clusters and the existence of clusters and their uniqueness is also true for semantic rank. Except that now we can, maybe I should say the clustering algorithm. I mean, let's not get into that. It's true, but yeah. Except now, so now the algorithm, the sketch we had for finding the set B that preserve the cluster. Now this thing works. We just start with the empty set, and we add one variable at a time. And each time we look at the polynomial we got, and we find the clusters, and we save it. And then we try to see if we can, if we add another variable, does something change? Like maybe there's another cluster, maybe some cluster splits into two clusters after we add a variable, or maybe they merge, or maybe the rank of a cluster increases. All those things can happen. So we just do it. We add one variable at a time until nothing happens. And then one could show that the clusters of F, the big F, and F restricted to this small set of variables are in one-to-one correspondence in the sense that each cluster of the small polynomial is a restriction of a cluster of the large polynomial. So it's really the same thing, but like a mini version of the large polynomial. Yeah, so I mean, yeah, I thought this talk was non-technical. Somehow now that I say it's a bit more technical than I intend, but believe me, it gets much worse. So I will spare you the details. So even showing those things that you can find a variable that increases the rank, that this process terminates, these are all things that you have to prove. It's not super complicated. It just takes some space. So, but this solve too, and eventually, yeah, we can bound the size of B, the number of variables that we need to project onto, by some k to the k to the k, something like that. And then we continue in a similar manner to the previous algorithm. But there is this issue that everything that they prove for syntactic rank, we now need to adapt to semantic rank. I have a few minutes. So I mean, I can show you again, not in a technical level, what do we do after we have this. So I have some slides on it, which I wasn't sure I would have time to, but since I have a few minutes, let's do it. So we have black box access to some restriction of a polynomial. I call it G because it's not F now, it's some cluster of F. So it's not necessarily F. And in order to learn this, we want to be able to evaluate G on arbitrary inputs. But we don't have G, we only have a restriction of G. Now, what does it mean? A restriction? It means that these variables are all fixed to alpha and these variables are still free. So if it happens that I want to evaluate G on an input that agrees with alpha on anywhere except B maybe, then I'm good, right? Because I have the exact restriction that I need, right? So if I want to evaluate on beta, but beta agrees with alpha anywhere except maybe B, here I still have variables that I can change and evaluate it. I have the restriction. So this is just a almost trivial statement. But of course, not all inputs I would want to evaluate are of this form. I want to evaluate at arbitrary points. Let's first assume that beta is different from alpha in just one coordinate, just some coordinate outside B. So in this case, what I can do is I can add J to the set B and learn everything again. And now I have the restriction to B union J. I can match them with the clusters, with the old clusters I have. So now I can just I can replace the J coordinate with whatever it needs to be. So this is something, if it only differs in one coordinate, this is something that I can do. But now let's say it differs in many coordinates. So I can do it, I can replace, well, I can try to replace it one by one and do the same thing. The only issue is that this alpha is not arbitrary. It needs to be, we pick it at random. It needs to satisfy some conditions that it satisfies if it's random, but then when you start to replace things, it's not clear that it satisfies them. So it could be that you are lucky and everything goes through and everything works and you are lucky and it works. And if it's not true, there's a very cool trick that you can do, that you can sort of do using some decoding algorithms for error corrected codes. You just you pass a line through alpha and beta, and you show that most points on this line is good, are good, but some points could be bad. But then you do some error correction, and you obtain the right value. So again, super sketchy and super high level, but nice ideas there, and eventually it works. And now, we get this restriction of G to a small subset, but using these ideas, we can actually evaluate the big polynomial G on every input that we pick. And then we just learn it using the low degree algorithms. And once we have all the clusters, we just sum them, and that's the polynomial. That's all there is to it. All right, good. So let's finish with some open problem. So yeah, one issue is that our algorithm is randomized. It doesn't feel like it must be random. Like it feels like it can be de-randomized. We use randomized in a bunch of places. It's mostly to pick again points that don't satisfy some polynomial conditions. And maybe there are ways to find them not randomly, but pseudo-randomly using some polynomial identity testing tricks. Yeah, well, this is a workshop on tensors, but there are circuits that are not multilinear, and they are interesting. And we use multilinear in a bunch of places just because it's convenient. Again, it doesn't feel like it has to be like that. I mean, it should be possible to do this. And yeah, like I said, there's a question of how large K needs to be before tensor becomes NP hard, which again, the difference between what we know is hard and what we can show is easy I mean, there's a large gap, and trying to bridge this gap is a nice open problem. So yeah, that's it. Thanks for listening. Yes.
So you mentioned the TK times 40n. What is the
So it's oh, the degree of poly n. Yeah, I don't know. It's not. I don't think it should be that I mean, that part shouldn't be terrible because but I don't remember. Well, 10 is a big number. I don't know. I mean, yeah, I mean, yeah, I don't remember. It should be possible to figure that out, but I don't remember right now. And the T of K is like, again, maybe 4 times exponential in n or something like, in K or something like.
I mean, I guess it's easy to see that for any fixed K, there is a randomized, there is a deterministic algorithm that tests whether a tensor has a deterministic polynomial time algorithm that tests whether a tensor has rank amongst K. But
Why is it easy?
because it's given by some finitely many equation. There exists. I'm not saying that I can run out the algorithm, but it's given by finitely many equations, and these equations that you have to test.
But is it easy to evaluate these equations?
Yeah, it's just, but that's probably a different game from what you were saying.
Yes, we have parameters. A and D. We are assuming K to be small. N and D can grow. Right. So your equation.
So N and D can go.
Yes.
Yeah.
Yes.
Oh, I see. So that's a difference.
Yeah.
Of course, if D is also fixed, it's E.
Yeah. Then.
But okay, so D is growing, and then but even then, so do you ever contract to go to lower degree? Because even then we know that if you fix, that's right. If you fix K,
Okay.
well, maybe we should take this offline.
It's a good question. More question. Thanks.